Another property that we could measure based off of the intermolecular forces is the vapor pressure. So first we just need to talk about what is vapor pressure. Well, basically, at any given temperature, some of the molecules that are on the surface are going to have enough energy that they could escape from the surface and become a gas. We call that gas a vapor. Specifically when it's a gas of a liquid that is right above it. So if I had a beaker of a liquid, some of those gas particles are going to be moving fast enough to have enough energy to escape. Because we have this situation here where we have a distribution, when I have a high temperature, remember this from previously, we have more molecules that are shifted over to a higher temp. When I am cooler at low temperatures, I'm shifted over on average to a lower temp. So if if this is the amount of energy here that it takes to escape into the gas phase from the surface, then you can see that when I have a cooler situation, a smaller number of particles are able to escape compared to when I have a hotter temperature. I have more molecules that are able to escape into the gas phase, which makes sense, right? When I'm hotter, things evaporate easier. So as the temperature rises, the fraction of molecules that have enough energy to break free increases, and then we're going to have more molecules escaping from the liquid into the gas phase. So let's go down here and check it out. Initially, I have an evacuated flask, nothing's in it. And once I put the liquid down into it, in this case it's ethanol, initially it's just going to be all liquid, but as time goes on, the molecules with the high kinetic energy are able to escape, and they're going to go into the vapor phase. At some point, the molecules in the vapor phase are also going to crash back down into the liquid, and it's possible that when they do that, they get reabsorbed or condensed back into the liquid. This is going to continue to happen where molecules escape and then molecules recollide until we reach an equilibrium state where the amount of molecules leaving into the vapor phase is equal to the amount of molecules recondensing back into the liquid phase, and we get a steady vapor pressure. So the vapor pressure is the amount of pressure that those vapor molecules are exerting on the surface in this closed container. So you can think about it. If I have a molecule that has a really strong IMF, right? It's really strong IMF, let's say hydrogen bonding. It's going to be really, really difficult. It's going to require a lot of energy to get into the vapor phase. So we're not going to have very many able to do that. So our vapor pressure, when I have strong IMFs, my vapor pressure is low. We call that PVAP because it takes so much energy to get up there. When I have weak intermolecular forces and I'm really volatile, meaning I can evaporate easily, then I'm going to have a lot of molecules that are able to get into the gas phase. And so that means I'm going to have a lot of pressure, so high vapor pressure. So it's basically inversely related to the boiling point. When I have strong IMFs, I have a high boiling point or melting point. But that also does mean that it's hard for those molecules to boil, so I'm not going to have a lot of vapor. Same thing here. If I have a low intermolecular forces, I have a low boiling point. It's really easy for the molecules to evaporate, and so I'm going to have a higher vapor pressure. So as more molecules escape into the liquid, the pressure they exert is going to increase, and then they're going to keep doing that until they reach this dynamic equilibrium where the molecules that are evaporating and the molecules that condense back in are happening at the same rate. So it's going to keep happening, but we're going to look like we just have a singular vapor pressure that stays constant. So we can use the vapor pressure and relate it to the boiling point. Basically, the boiling point of a liquid happens when the temperature at which the vapor pressure is equal to the atmospheric pressure. And we normally don't think of boiling point related to temperature at all, but it is. We are going to have to heat up the liquid enough to where it increases its vapor pressure. We get more and more molecules into the vapor phase, and eventually that vapor pressure equals whatever atmospheric pressure is, and when that happens, the liquid will boil. Normal boiling point is the point or the temperature at which vapor pressure is equal to 760 torr or 1 atmosphere, so it's basically at sea level. Here we can see this diagram. What we see here is that here's our vapor pressure versus temperature, and we can see that when we have something like diethyl ether has a low boiling point, right? It's about 34.6. And so we can see at a really low temperature, it has a pretty high vapor pressure. So once again, we're seeing low boiling point equals high vapor pressure. And so we can continue for some of these other molecules that have a stronger IMFs, such as ethanol or water. Let's do water. Water has a really low vapor pressure because it has strong IMFs at low temps. As we heat it up, we're exciting those molecules, especially at the surface, and so they're escaping into the vapor phase, more and more of them, until eventually it reaches atmospheric pressure. This line here represents when our vapor pressure, when the vapor pressure line crosses this atmospheric pressure line, that's the temperature we can extrapolate to down here for our boiling point. So that plot that we see up here, it has an exponential type of relationship with the temperature. And so basically what they do is they take that curve that it fits to, they take the natural log of the vapor pressure here, and they take 1 over the temperature. Don't worry about that, it's a little confusing. And what happens is they get this plot that linearizes the relationship between pressure and temperature. What they get is that the natural log of the pressure is equal to negative enthalpy of vaporization divided by RT plus a constant. I like to write this more like natural log of P equals negative delta H VAP over R times 1 over T plus a constant. Because then you can kind of see this. This is your y-axis here. This is your x-axis here. And then you can see that the slope is equal to, whoops, I want to include the negative. The slope is equal to negative enthalpy of vaporization over R, and then C is the intercept, and C is a variable we don't really worry about. So we can use this. If we were to take a substance, put it in a closed container, measure the vapor pressure at a bunch of different pressures, we can take all of those pressure values and do the natural log of them, and then take all of our temperatures we did in Kelvin and do the inverse of them and plot it, and we can, when we get the slope out of that, we can get the delta H vaporization value. So that's a pretty cool way that scientists are able to determine the vaporization enthalpy. We can take the 2-point version of this equation, which I strongly recommend using, and you'll use it in some problems in your homework when it gives you, here's a vapor pressure at this temperature, here's a vapor pressure at this temperature. What's the enthalpy of vaporization? Or it might say, here's a pressure and a temperature and enthalpy of vaporization. What's the pressure at this other temperature? So it's the natural log of pressure at condition 2 over pressure of condition 1 equal to delta H VAP over R times 1 over T1 minus 1 over T2. So notice here I have condition 2 going on the top and on the back for temperature. Pressure 1 is going on the bottom, but it shows up for the first one for the temperature. So keep that in mind. If you do it opposite, you'll just get a negative value and you'll get the value wrong. So what we're going to do now is we're going to try to estimate the boiling point of diethyl ether under an external pressure or an atmospheric pressure of 0.8 atmospheres. So we could use our diagram here. We want to know, here's diethyl ether in red. we want the external pressure to be 0.8 atmospheres. So I'm going to need to take 0.8 atmospheres and convert it into torr because our units for our y-axis are torr here. So we're going to do 1 atmosphere is 760 torr. And that gives us a pressure of 608 torr. So what we can do to find the temperature at that point is find our 600 on our graph. It's about right here. We're going to go over until we hit the curve we want. We want diethyl ether, so here we hit it around a little bit above 600. Now I'm going to extrapolate down, the hardest part is doing a straight line, to the temperature axis, and we can see it's maybe like, I'd say 28 degrees Celsius, and that will be determining on your how you drew the line and your perception, but it's rounding, so a little bit. Maybe you said 27, maybe you said 30, either one, it's fine. And then we also want to find here, we can do the opposite way, where if I want to find the pressure where ethanol boils at 60 degrees. So now I can take ethanol, which is this orange curve. I'm going to extrapolate from 60 degrees up to ethanol, and now I'll extrapolate over to the with the vapor pressure axis. I did a little bit further down, so we can see that the vapor pressure is about maybe like 320. About 320 torr. And once again, maybe you said 330, maybe you said 340. I don't know, it's an approximation, so give your best guess. Now we're going to do some calculations using the Clausius-Clapeyron equation. This says that gasoline is a mixture of hydrocarbons, which is a major component of which is octane. This is big old hydrocarbon here. Octane has a vapor pressure of 13.95 torr at 25 degrees Celsius and a vapor pressure of 144.78 torr at 75 degrees Celsius. Calculate the heat of vaporization. So I gave you a heads up that might happen. So the first thing I like to do is combine my terms. So I'm going to call P1 equals 13.95 torr. T1 equals 25 degrees Celsius. I'm going to go straight over to Kelvin, so 298. P2 is 144.78 torr. And T2 equals 75 degrees Celsius, so add 273, and we should get 348 Kelvin. All right, so now what we're going to do is we're going to plug into Clausius-Clapeyron. We have 2 points here, so we can use a 2-point equation, which is natural log of pressure 2 over pressure 1 equals delta H VAP over R times 1 over T1 minus 1 over T2. So we can plug in our values here. We're going to get the natural log of pressure 2 we got as 144.78 torr over pressure 1 is 13.95 torr equals delta H VAP is what we're solving for. We're going to use our energy R, which is 8.314 joules per mole Kelvin. And we know we're going to use energy R because we have an enthalpy term, which is energy. We'll do 1 over T1, which is 298 Kelvin, minus 1 over T2, which is 348 Kelvin. So first thing I'm going to do is actually calculate this term, that's just a number, and I'm going to calculate this term, which is also just a number. And what I get is the natural log portion is 2.34 and unitless, and that's going to equal delta H VAP over R, 8.314 joules per mole Kelvin, times by 1 over those numbers. So when we subtract those two numbers, we get 4.82 times 10 to the negative 4th. And that will be inverse Kelvin. So what ends up happening is our Kelvins cancel out here. And then this, again, is a number. So we can take our value we just got, 4.82 times 10 to the negative 4, and divide by 8.314. And so we get 2.34 equals delta H VAP. Whoops, no divided by because I'm combining them all together. So times by 5.799 times 10 to the negative 5. And then we're going to divide that whole thing over. So we'll divide that guy down. So we'll do 2.34 divided by 5.799 times 10 to the negative 5th. And those units were mole per joule, which will then flip up. So we'll do 2.34 divided by that. And we get our delta H VAP being 40,350 joules per mole, or we could divide by 1,000 and get 40.35 kilojoules per mole. So a lot of algebra there, kind of annoying. A lot of algebra, but definitely, doable. You just have to rearrange a bunch. The next one is calculate the normal boiling point of octane. So now that we have delta H VAP, we could use any one of our pressure terms up here. Let me switch to green. We can use any one of these. I'm going to just do pressure 1. And we know that here now I'm going to say we want to find the normal boiling point, so we're trying to find T2. And we know that boiling point happens when pressure, so pressure 2 is going to be 760 torr, and we're trying to find temperature 2. So let's plug in again. So fun. So do natural log of pressure 2, using this equation right up here, natural log of pressure 2, which I'm going to call 760 torr, divided by pressure 1, which I'm using our first condition, so 13.95 torr, equals delta H VAP, which we just calculated. Let's use it in the joule form because that's what the units are going to cancel out. 4,350 joules per mole over R, which is 8.314 joules per mole Kelvin. So our joules per mole will cancel out, times by our temperature. So we're going to do temperature 1, which we have as 298. So 1 minus 298 Kelvin minus 1 over T2, which we're solving for. So once again, this is a number. This is a number. We're going to calculate for it, and then we're going to solve for T2. So we're going to do natural log of 760 divided by 13.95. And what I get is, let's write this in another color, 3.998. That's going to equal 4,350 divided by 8.314. And you get, for this part, 4853 times 1 over 298 minus 1 over T2. So now we can solve for T2 by dividing that over. We're going to divide 3.998 by 4853. Cancel that out. So 3.998 divided by our answer. So we get this equals 8.24 times 10 to the negative 4, and it's going to equal to this thing, 1 over 298 minus 1 over T2. All right, so 1 over 298 is a number. I'm actually going to subtract, 1 over 298 over, so we're going to get minus 1 over 298. So I'll take my 8.24 and I'll subtract 1 over 298, and you end up getting a negative 2.53 times 10 to the negative 3rd equals negative 1 over T2. The nice thing here is our negatives are just going to cancel each other out, so we just have positive. And then to get T2 on the top, we're just going to do the inverse of both sides. So I'm going to take my value, and you can find on your calculate x to the -1. You'll see that sometimes. And I'm going to get that my second temperature is 395 Kelvin. All right, so again, a lot more math. We needed way more room. Sorry about that. But that makes sense that at 348, we hadn't got to boiling yet. Our vapor pressure wasn't 760, but once we got to 395, that's when it does hit our normal boiling point and our octane will boil.